In July of this year, we invited people to show off their graphical prowess using a rapid prototyping and development tool called Gigi, which is developed by Seed's Future Graphics Group. Not only did this give people a forum to learn new things or share interesting things with others, this helped Gigi mature to prepare for open sourcing. We received 13 amazing entries, including differentiable rendering, Perlin noise-based explosion effects, ray-trace particle systems rendered in screen space, and not yet published research papers on physics simulations. A few people agreed to make lightning talks about their creations, and without further ado, here they are.
Reconstruct material is a simple Gigi technique implemented to explore differentiable rendering, and it uses slang. The goal of the technique is to find material attributes given a bunch of input images. This is one input image with one view direction and one light direction, but the algorithm can query any view direction and any light direction. The material attributes are stored in two textures. You can see the left top is the albedo color or base color. The top right is the normal, encoded as a color. On the bottom left, you can see the roughness between 0 and 1. And on the bottom right, you can see the metalness. This is the reference. So this is the values that we ideally would like to approach to, but the algorithm can only fit going close to that, but it doesn't completely reach them. But that's the target. So inside the editor, you can see that almost everything is implemented in a single pass. That one computes the gradient and updates the state. But there's another compute shader that is visualizing everything in tiles so that the user can observe what's the current state and how does it compare to the target. And the compute gradient has some resources, but they're just to store the gbuffer and to debug it. In the shader, you can find the call into the BRDF function. This is computing the material response based on the material attributes in the gbuffer, the light direction and the view direction. And then this color that is computed is compared against the target color. It could come from input images, but at the moment it's also computed. And that error that is computed here, the algorithm tries to minimize that. So with the differentiable rendering or slang, it figures out the gradient of those variables, state A and state B, which are representing the gbuffer. And then it pushes down here in the shader, it pushes it towards less error. And in order to compute a gradient, it has either the method of backward or forward. And so you can go into those branches. And when it pushes it, you can also press the button for resetting. Then you see that it resets it and starts it from scratch. Inside the viewer, you can click on the overview node, and then you see this image that has 3 images on the left, which are the reference or target gbuffer and shaded result. And on the right side, you can see the current state of the reconstruction. And depending on if you use the forward or the backward method, it has a slightly different result. You can always click on the reset on the variables left top to kind of restart the process so you can see how it slowly refines towards the right solution. But there's some noise left, and it also slowly converges. It's a very simple gradient descent implementation, but it also has some noise as a part of the implementation. So that's why there's also noise in the image. So the purpose of this was to see how easy it would be to run differentiable rendering outside of the usual Python frameworks. And thanks to Slang and Gigi, that was rather easy. You can use that as a sample starting point for your own experiments, but it's by no means a mature implementation that should be used, but it's a good starting point for your own experiments.
Hi everyone, my name's Andrew. I'm going to talk about my project in Gigi, which is implementing a FFT. So my first time kind of doing compute shaders, and Gigi made it really easy. And I'm just going to walk you through some of the steps that I did. So our first node here is our real valued FFT. This is kind of the basis of the whole thing. After some reading some stuff and trying to figure out how I wanted to approach this, I've settled on a node that implements what it needs to in 256 threads. So it hard codes an assumption that the wave size is always 32. And that's a good assumption on some hardware, and it's not so good on other hardware. But I'm trying a couple different things like group shared memory and wave intrinsics. And so starting with a very simple assumption that the wave size was always 32 was a good starting point. And so that's kind of baked into the discussion today. So 256 threads, so 32 by 8. Another way to say that there's 8 waves going on simultaneously. And all it does is take one input buffer, which is a bunch of floats, which is our real values, and then an output buffer, which I've defined a custom type, which is complex here. It's got one field, which is a real, which is called real, and it's a float. Another one, it's called imaginary, and it's also float. So if we go into the code, this is our real valued FFT. And this is where we define our group shared memory. So I'm defining a 2-dimensional array, 32 by 32 floats, one for real, one for imaginary. So in total, this gives us 8,000 bytes of group shared memory usage. So just something to keep in mind. There's limited access to group shared memory. I think the highest you can do is 32,000, which we'll see later on. So this is using a significant chunk of group shared memory. And when you're using group shared memory, you want to be aware of bank conflicts. So we have a wave of numbers, and we're going to access memory in 2 axis patterns. So first axis pattern is a single wave will read all the values in a row. And that one's pretty easy to handle. The second one is a single wave will read all the values in a column. And that one's a little trickier, because if you did this kind of the straightforward way, then what would happen is that when you tried to do that column access, every single thread within the wave would try to access memory that was from the same memory bank. And when that happens, the GPU will run those sequentially. And so you won't be able to get as fast as you otherwise would. So you can do a little trick where you change the individual rows such that they're offset. And so you can access any particular row or any particular column from within the wave, and it's fine. So that's what this function attempts to do. I hope it works properly. And then we're doing a little trick called the Bailey FFT, which is where you break your larger FFT down into 2 components, typically square. So our 1,000-point FFT is broken down into 32 by 32. And so what we do is we do a 32-point FFT of all the individual rows. We do a twiddle step, which is just a complex multiplication with a known value for each element. And then you do FFT 32 for all the individual columns. And at the end of the day, the end result is the same result you would get had you done a larger 1,024-point FFT. So we read from memory and copy it into group shared. And we're trying to do this in such a way that all of those reads are coalesced. So every single read is sequential, from the one before it. So we're trying to maximize that as much as possible. Then we do that 32-point FFT of all the individual rows. And then this function itself builds in that twiddle step, which is, again, is just a complex multiplication with a known value. And then we do the individual columns. The only real difference here is there's no twiddle step. And then we copy it all right back into the output buffer. So fairly straightforward. Where the magic happens is largely in this FFT32 function, which does use wave intrinsics. So wave intrinsics allow you within a wave to access values from other threads within the same wave. And so we use that to our advantage here, such that, the first thread within the wave access what it needs to from neighboring threads in order to calculate the final result that we want on the end of the day. And we want a 32-point FFT. So to do that, we do it in 3 parts, a radix 4 FFT, another different radix 4 FFT, and then finally a radix 2 FFT. So 4 times 4 is 16, times 2 is 32. The end result, the math works out such that it's the same as an FFT 32. So if we pop into the viewer, which is a great way to debug compute shaders like this. We have our input values, which are just sequential numbers here. And we have our output values, which are complex values in this case. So if we want to do a sanity check, we can use NumPy. We can ask for the FFT of 1024, sequential numbers starting at 0, and then we can compare. So if we look, we see pretty close. Obviously, there's some numerical error. So our FFT implementation is using, single precision floating point values, is using fast floating point math, so it's not the most accurate. So some deviation from NumPy is expected, but overall we're getting exactly the numbers we want. So the next step, once we have an single dimensional FFT working, we might want to do a two-dimensional FFT. So that's what this would look like. We're doing the very simple thing where you do all the rows for one dimension and then you do all the columns. But of course, accessing columns like that from global memory would be a very large stride, and we want to be coalesced. We want to read sequential as much as possible. So instead, what we're going to do is we're going to do those rows, and then we're going to take that whole thing and transpose it. So the rows become the columns become the rows, and then we do the same FFT, this time still on the rows, but those rows represent what was previously the columns. So that's how we do our 2D FFT. And an interesting thing about the second one, so you do the first FFT, the inputs are real values. The output of that is a complex value. So the second FFT actually operates on complex values. There's not much more to that. The code is basically the same. It just originally we defined the imaginary values to be 0, and here we're just reading them directly. So once you have that working, we have this working on buffers right now, but what would be really interesting is to have that work on textures. So we could have an input texture and do an FFT on it. And then why would we want to do that? Well, an interesting property of an FFT is if you do multiplication in the frequency domain, that's the same as convolution in the spatial or time domain. So we can do this to do things like blur and other things that would typically be done with convolution, but we can use an FFT to do it. So we take our input texture, we split it into red, green, and blue components. We do an FFT on those. Once we have the frequencies, we multiply by our blur representation in the frequency domain, and then inverse FFT to go backwards from frequency into spatial. And then we have the result of doing a convolution, assuming we've sized everything appropriately, of course. And then this does essentially that, but with some optimizations. So we're combining red and green channels here. The red channel goes in the real axis and the green channel goes in the imaginary axis. That lets us use one FFT for both of those channels. So that's a little bit faster. We're out of channels to share blue with, so blue's on its own. So this is an area for improvement because we're kind of wasting half of the FFT here that we could have otherwise used. Another optimization that's going on is this is the horizontal FFT, but it's also multiplication by the Gaussian frequency domain weights. So we fuse that complex multiplication into the last step here. You could take that even further if you wanted to infuse a couple different steps, like the first layer of this inverse FFT could also be fused in. That would be really interesting to try and see if you could reduce this down and be even faster. So let's see what this looks like in Gigi Viewer. We'll start with an input texture. So our input texture looks like this, and it's of size 736 by 736. And at the end of the day, what we have is we've multiplied by a Gaussian kernel, and we've increased the size of our texture. So what was 736 by 736 is now 1024, 1024. And the difference is the size of that Gaussian kernel that we're multiplying by. So our Gaussian kernel makes this nice and blurry. So we're implementing a Gaussian blur here. But of course, you don't have to use a Gaussian function. You could use anything. And there's all kinds of neat effects you could do. It's essentially implementing convolution. So anywhere where you'd want to implement a convolution, you could use something like this. So to step this up a notch, you might be interested in doing a larger FFT. Certainly, if you're dealing with 4K textures, 1024 isn't going to cut it. So we've implemented, just like we did here with the 1000-point FFT in one dimension, we also have a 4096-point FFT in one dimension. And we're doing the same trick where 1024 was 32 by 32, 4096 is 64 by 64. And otherwise, the code is pretty similar. We're kind of maxing out the available group shared memory here, though. So in DirectX 12, the largest we can request is 32,000 bytes of group shared memory, I believe. And that's what we're using here. So we can't really request any more group shared memory. And I found out in trying to implement this that my implementation uses a lot of registers. So we kind of run out of registers before we run out of group shared memory. So you're not even necessarily making best use of all the resources available to you. So there's lots of room for optimization. But you can compare the 1D case, you can compare the 2D case, you can look at the inverse transforms, and of course you can do the same texture trick. So I've removed, for the sake of simplicity, some of those optimizations here. So there's lots of room for improvement. We're just doing the red, green, blue channels all individually. There's no fusion going on. And if we look at what that looks like in the viewer, we'll see we have a much bigger output image here, and it is partially blurry. And the reason it's partially blurry is that the input texture is now, 3840, which is kind of representative of, the width of a 4K screen. And so, percentage-wise, our Gaussian kernel is much smaller because it has to, fit in 4096 by 4096. So as a percentage of the overall image, it's much smaller. So the blur is not as strong, but overall the same process applies and it's the same result. Thank you, and I hope you enjoyed my talking about compute shaders implementing an FFT.
My entry for the jam was a Gaussian splat viewer. Gaussian splatting is a new 3D rendering technique for capturing a scene with multiple photos or videos, and then using that input data to learn a representation that can be used for 3D rendering from novel viewpoints. The idea of the paper is to represent the scene using 3D Gaussians, which can be thought of as points or particles in space, and these have various different parameters associated with them. And then using differentiable rasterization combined with stochastic gradient descent, the authors learn a representation that can then be used with a renderer to allow real-time navigation. So my entry for the jam was to implement just the visualization part of this, not the differentiable rasterization part. I'd like to give credit to the authors of this repository, Unity Gaussian Splatting, available on GitHub under an MIT license. This is a really nice implementation of the real-time visualization part in Unity. So it just takes the already produced Gaussian splat model file and is then able to render it, and you can use a 3D camera to navigate around. So my entry was a Gigi port of this repository, basically. Moving across to the viewer, I can just give an overview of how this works. Over here on this side, you can see that there's some input data which comes from the trained part of the Gaussian splat. These are passed to a compute shader which transforms that data as parameters for the rasterization that will later be performed. The rasterization is going to be rendering lots of alpha blended quads, and these quads need to be rendered in the correct order for the rendering to appear correctly. So the way that's done is using a compute shader, which calculates the distance of each splat from using the latest camera transformation. And then there's this collection of subgraphs which implement the sorting. This is based on a sort routine from AMD, and it uses a nice feature of Gigi called subgraphs. And what this means is that each individual node here is doing the same graph, but with different parameters. And if I double click on the subgraph, it'll open in the editor, and I can see that each individual subgraph is 5 different compute shaded dispatches in this case to sort 4 bits at a time. This could actually be improved now. I just didn't have time for the jam, but this could actually, these 8 nodes that sort 4 bits at a time could be converted into another subgraph, and Gigi supports subgraphs within subgraphs. So from the top level, there would just be one sort subgraph. And so the output of the sort routine is an array with the indices ordered so that the rendering will appear correctly from the point of view of the camera. And these are passed to a draw call, an instance draw call, which performs the rasterization. And then finally, there's a compose to screen pass, which does some color transformation. So there's a set of input data required. And if I open the viewer, you can see that this data would normally need to be provided by the user. But in order to give the user the best experience possible, I use another really nice feature of Gigi, which is the Python scripting to simplify and make it as easy to use as possible. So I can just bring up the Python script that I use to do this. So I need to perform some transformation on the original ply file coming in from the trained model data. And what I do is I actually use a C++ executable I wrote for the jam, which performs the data transformation. There's no real reason why this couldn't be done in Python other than I've just got more familiarity and it's faster to do in C++. So the source code of that is included in the jam entry zip file. And this is a slightly different implementation from the jam entry. At the time of the jam entry, it was not possible to use API call get script path. This will return the folder that the Python script is executing from. So at the time of the jam entry, I would have had to bring up 2 dialogues to display, one to pick the path of the executable and another to pick the apply file. Whereas in this case, because of this get script path, I can just call one dialogue to load the apply file, and that's a very nice user experience. So the source code of this is available. It's just a simple console application that takes in the input path to the apply file, does some transformation on the data, and eventually outputs, writes some data to disk, and also outputs some information that is later used by the Gigi Python script. These parameters are passed from the output, and I then make these host calls, which is using the Python API from Gigi, and that is to set up all the different data types, all the different sizes, channels, and all the information that's required. And now I can go back to the editor and I can just show how this works in practice. So from the editor, I can just click Run Python Script, and I can select the Python script. This will bring up a PowerShell. This executes a dialog picker, and it allows me to select the ply file. This will take a few seconds, and then once it's loaded in, it should be displaying. Yeah. And then you can just use the normal camera controls to navigate around. So this is available on the Gigi Jam website if anyone's interested in playing around with this. There's some instructions about how to use it, and there's also a link to some trained Gaussian splat models that can be used with the viewer. Thank you very much for your time.
Hello. For my Gigi Jam entries, I wanted to explore the chaos game in 2D and 3D for making fractals, as well as looking at L systems. So first off, we'll look at the chaos game in 2 dimensions. So with the chaos game, you start by making a couple vertices. And so here's a triangle made with the red, green, and blue vertices. And what you do is you pick a point at random, one of these vertices. From there, you pick another point at random and move half of the way towards it. And we can do a step. And so either it picked the green or the blue, and it stepped halfway towards it, and it's right here. So that was the first step. So for the next step, it's going to pick another vertex, and it's going to move halfway there. And so we can click step again, and it made another one. So I guess it picked blue. And you can click step again, and it chose blue. And now it's finally moved over here a bit. And as you step more and more and more, it'll start to fill in. In fact, we can just set step to 0 and play. And you can see that it slowly starts to fill in into a Sierpinski triangle, the fractal. Now this is pretty cool, but even with VSync off, is VSync off? Oh, it's on. Even with VSync off, and so it's running almost at 1,000 frames a second, it takes quite a long time to fill in. So to render these faster, what you can actually do is instead of just having one point moving around at a time, you can have like 1,000. Let me reset the variables to default and play. And yeah, you can see it immediately filled in, and we have our Sierpinski triangle. And so that's quite amazing that just randomly selecting a vertex and moving halfway there can do such a cool thing. But you could actually have more or fewer vertices and change the amount that it moves from the current position to the next position, and you can get some other fractals. So we'll run some Python scripts to check that out. So this one was Sierpinski triangle. And so we can also do a Sierpinski carpet, which this one, it has 8 different vertices, and it moves 2/3 of the way from the current point to the next point. And then you end up with this Sierpinski carpet. These Python scripts, all they're doing is they're setting up these parameters right here. So you could type all this stuff in by hand as well. They're just here to be helpful. And so you can do this with like a heptagon and get this kind of a fractal, or a hexagon, a pentagon, or even that shape. And so yeah, this is the Chaos Game 2D demo. And so next up, let's look at the 3D demo. Here we have the same setup, but now it's in 3D instead of 2D. And instead of having a simple triangle, we have a tetrahedron. But it works the same way, where it starts at a random vertex, picks another random vertex, moves halfway there, plots a point, and rinses and repeats. But this time being in 3D, we can go all around it. I guess I could show you how this works in the editor. I'll pop open the editor. And essentially, this is the graph in Gigi that makes it. So we have an initialization pass that only happens on when frame index equals 0. And then this compute shader for step happens every frame. And we'll pop that open. Just double click it. And so what this does is it has state about where it is, where the point is in space. and then it picks a point at random to head towards, and then uses lerp to head towards there, and then writes another position out. So that's all there is to that shader. And then we have a rasterization call to draw those points as points. And then we also have another draw call for when we want to do red and blue 3D mode, and then to combine those when that's true. And so, yeah, you can turn on red, blue 3D mode over here, just clicking this box. And then if you have red and blue 3D glasses, it'll pop out at you. And once again, you could make different shapes by entering different points or different fraction amounts. And it uses multiple cursors. Something cool about Gigi Viewer that's kind of fun when you're developing, you can pop open the render graph here, and you can see various buffers. Like here's one of the constant buffers, and then here's one of the buffers that it uses for, what is this one? The points. Okay, so yeah, this holds all the points. And you can even see in the profiler how much time things are taking in the CPU and GPU. And next up, let's look at L systems. So L systems, much like the chaos game, have been around for quite a while. Probably, I think, like the 60s or 70s. Yep, here it is, 68. And they're called L systems because of the last name of the person who invented them, Lindenmayer. He was a Hungarian biologist and botanist. So that's interesting. So L systems are basically string replacement, where characters in the string are commands, like draw one line forward, or rotate 30 degrees, change a color, things like that. And so, yeah, the Wikipedia article on L systems is pretty informative. There's some great videos on YouTube as well. But like, here are some examples where if you have variables A and B, these are the characters that you can have in your string, and you start with the axiom of A, so your string starts with A. Then you have the rules that A becomes AB and B becomes A. Then this just shows you how the string evolves over time. And scrolling down a little bit, you can see it can make some fractals and kind of some plant-looking things, which is pretty cool. And this right here, the Sierpinski triangle, that's what we're going to look at first. Oh, there's the dragon. That's cool. Okay, so yeah, so string replacement on the GPU is a bit interesting because the GPU is parallel by nature, but string replacement is serial. So I didn't really do anything super special in the implementation. You can check it out. I'll just flash it real quick. I guess there's kind of a lot of the stuff. We got initialize step. And then, yeah, we copy the symbols and then make the line list and render bounding box, red, blue 3D, and combine them, blah, blah, blah. I guess, yeah, so there's some stuff in there, but a lot of it has to do with rendering and less with the string replacement. I think make line list is where the string replacement happens. Spin a little bit. Yeah. So there's like commands and stuff. I won't explain how the buffers work and stuff, but yeah, check it out. There's comments and things. So yeah, so we can start off with the Sierpinski triangle. We're just going to click initialize and then step, and it's done one level of a replacement, and we can press step again, and it does another, and eventually it starts looking like the Sierpinski triangle, which is interesting because it's just made up of a string of commands of, like, draw forward, turn left 30 degrees, draw forward, turn right 30 degrees, etc. And so, interestingly, we can zoom in. Yeah, okay. Yeah, we can just fly inwards. Never mind. And we can see that this is where the line starts, and then it goes up all through this triangle, and then this is where the line ends over here at the other side. But when you zoom out, it looks like a Sierpinski triangle, which is pretty interesting. But there's some other examples here as Python scripts again. So that was Sierpinski. We also have snowflake, so we can initialize. Step starts with triangle, step, 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 step. And it's like the old Koch's or Coach snowflake. And yeah, basically that red, this happens when it busts the buffer, and it's letting you know that. Okay. Next up, let's look at the Cantor set. It's kind of boring, but what it is it takes a straight line and cuts it into thirds, then removes the middle to make the fractal, which is Cantor's dust. And so we can just keep clicking that. And it's rasterizing these as line segments. And so yeah, you can zoom in, but it gets pretty aliased as well. And then lastly, something super cool. So we can start with a line and then kind of turn it into this wheat shape. And if we keep doing that, we get something that looks a lot like a plant. So it's pretty cool that L systems, they can make fractals, but they can also make things that look very organic, which makes a lot of sense that they were developed by a biologist. So that's my Gigi Jam entry. Thanks so much for watching.